Last couple of days, we've introduced the idea of gravitational fields. We defined a field as a line of influence that surrounds something. Now, when we're talking about a gravitational field, we're talking specifically about a line of influence that surrounds an object with mass. In other words, something that causes gravity. Draw a picture of the Earth here. The Earth has a gravitational field surrounding it, and the field always points toward the Earth. It looks something like this. We call that a non-uniform field. The field lines aren't parallel to each other. It's a non-uniform field. In other words, the field isn't the same strength everywhere. The closer you are to the producer, the closer you are to the Earth in this case, that causes the field, the stronger the field is going to be. And that should make sense to us, right? If we go up in a spacecraft far, far, far away from the Earth, then the gravitational field is going to get weaker the further we get away from the Earth. If I was to put an object right here, a big green ball right there. That's a really big green ball relative to the size of the Earth. What would happen to it if I just let it go? It would fall down towards the Earth. Good. What if I put it right here? It would fall down towards the Earth, right? But down towards the Earth would be this way. Always moves toward the Earth. Always experiences that force toward the Earth. Force. Okay. What's the difference between a force and a field? We said that these masses always exert or always experience a force toward the Earth. We're talking about gravitational fields here. What's the difference between a force and a field? What does a force need that a field doesn't need? Yep. Something to experience it, right? If we have this green ball right here to experience the field, then there's going to be a force. If we have this green ball to experience the field, then there's going to be a force also acting downward toward the Earth. But if we take this away, the experiencer away, there's still a field. The field's caused by the Earth. But if we don't have the object to experience that field, then we no longer have a force. So a force needs both a producer and an experiencer, whereas the field requires only the experiencer. Does that make sense? All right. Here's our little green ball again, our big green ball again. That big green ball experiences a gravitational field. Let's put it right here, actually, right smack in the middle of that field. It experiences this gravitational field right there. The Earth produces this gravitational field right there. If we have information about the Earth, Kathleen, if we have information about the Earth that causes the field, then we're going to use this equation to find the strength of the field, gm over r squared. If we have information about this guy, the one that experiences the field, we're going to use this equation, g is equal to f over m. Okay. In this case, the first g would be equal to the second g. The field produced by the Earth at that point would be the same as the field experienced by this big green ball at that point. So if we wanted to, we could set those two equal to each other. It's not very often we have to, but we could if we wanted to. Okay, let's look at a couple givens here. G is our constant. R is the distance from the center of the Earth, or the center of the producer, to the experiencer. And M would stand for? So what's M stand for? Mass, right. Mass of what, though? We get two masses here. We get the green ball mass. We've got the blue Earth mass. Which mass do we use there? Devin, which mass are we going to use there in this equation right here? The mass of the producer, the Earth, or the mass of the experiencer, the green ball? Yes, the mass of the producer. As opposed to down in this equation, where if we're using the experiencer equation, the one for the green ball, then we're going to use the mass of the green ball. So the mass of the experiencer. Which one should you use in a given question? It doesn't matter as long as your givens match up. Okay, if you have more information about what causes the field, the Earth in this case, then use the producer equation, the blue one. Okay, if you have more information about the experiencer, the green ball in this case, use the experiencer equation, the green one. Use whichever one fits, whichever one you have more givens for. Does that make sense? Ever a time when you're going to use both of those? Sure. Sure, it happens. Okay, what if, for instance, we were looking for force here? What if we were looking for force? What if we didn't know what G is? Well, maybe we could solve for G using this equation. And then we could set that G equal to this, and then turn around and solve for F. In other words, use both of the equations. Solve for G in one equation, and then plug it into the other equation. Okay, we don't do that often, but it seems to me on one or two of the homework questions we did have to do that. All right, speaking of homework questions, our homework was on page 218 and on page 220. Any issues with the questions on page 218, please? Who's got them done? All right, let's take a look at 2 and 3. Questions that are requested here. 2 says an 80 kilogram astronaut in orbit this far away from the Earth's center. Let's draw it out here, okay? Here's the Earth. Here's the center of the Earth. Here's our astronaut that's in orbit around the Earth's center. The distance from the center of the Earth to this astronaut that's orbiting around is 3.20 times 10 to the 4 kilometers, which, of course, we want to end up converting to meters. We'll deal with that a little later on. What's the field strength at that location? And what's the field strength if the astronaut was orbiting the moon with that separation distance? Well, this is the Earth, and the mass of the Earth is 5.97 times 10 to the 24 kilograms. All right, this is question A. When we go to question B, okay, all we're doing is changing the mass to the mass of the moon, which is, I'm not sure what it is, something to the 10 times 10 to the 22, I think. Okay, we'll deal with that when we get to it. Look, you want to find the field strength here. The field strength produced by the Earth where this astronaut is the same as the field strength experienced by the astronaut. What do you know more about? The 80 kilogram astronaut or the Earth? In other words, do the givens fit the producer equation better, or do they fit the experiencer equation better? It doesn't matter which one you use, as long as you have enough givens to fit it. Which one fits better? Which one fits better here, guys? Gm over r squared or F over m? Tyler, which one fits better there? First one or the second one? Yeah, looks like the first one. Okay, we know the distance from the center of the Earth. We know the mass of the Earth. Let's go with the producer equation. So let's say 6.67 times 10 to the minus 11 times the mass of the Earth divided by 3.20 times 10 to the, careful on this one, 3.20 times 10 to the 7. Good, because we're dealing with meters, not kilometers. Okay, we do the math there, and when we do, 2a works out to be 3.89 times 10 to the minus 1. The units could be newtons per kilogram, or they could be meters per second squared. It doesn't matter, because in the end, gravitational field strength is the same as the acceleration due to gravity. What is it on the surface of the Earth? About. We've used that a million times, right? 9.81. This is a lot lower. Why? Because we're a lot further away from the center of the Earth than we are right now as we sit on the surface. 10 to the 4 kilometers. 10 to the 4 kilometers. That's 32,000 kilometers. Do you know how high the space station orbits around us right now? 400 kilometers. That's it. That's it. It's 400 kilometers above. Okay, it's the distance between Okotoks and Edmonton, pretty much. Now, it's a lot easier to get to Edmonton than it is to get to the space station, but it's no closer, or at least not much closer. That's why gravitational field strength on the space station is quite a bit higher than it is here. All right, how would we do B? I'm not even going to go through that, but we'd do B in the exact same way, except that this number right here, the mass, would be the mass of the moon, whatever that happens to be from the table that I showed you yesterday. Is that okay? Who asked me for that question? Is that okay? What would we have done here Just a quick little change to this. What would we have done if they had have given you this distance, the distance from the surface of the Earth to where this astronaut is orbiting around? How would we change this question? How would we have solved it then, Kevin? Perfect, perfect. You'd have to add the radius of the Earth to how far he is above the surface. In other words, you need the total distance from the center to where the astronaut is. Right, Liam? Let's take a look at number 3 now. The highest satellites orbit Earth at a distance of about 6 times the radius of the Earth from the Earth's center. That's a big distance. Okay, that's a long way away. 6.6 times the radius of the Earth away from the center. What would the gravitational force on a 70-kilogram astronaut be at this location? First of all, astronauts don't orbit at that location. Astronauts orbit at the same altitude, roughly, as the space station. So that's about 400 kilometers. Now, if you go into the moon, then you'd be further away. But the last time that's happened has been 40 years ago, right? Over 40 years ago. But if there was an astronaut there, what would the force of gravity on the astronaut be? Here's the Earth. Here's the radius of the Earth. This distance right here from the surface to the center. Here's the astronaut up here. What's this distance right here from the surface to the astronaut? Tough question. What is it, Joe? Good. 5.6 times the radius of the Earth. The total distance from the center to the astronaut is 6.6. And that's the distance we really want there, right? We want to find the force here. Well, we know the mass of the Earth. It's 5.97 times 10 to the 24 kilograms. We know the mass of the astronaut is 70 kilograms. And we want to find the force experienced by the astronaut. What do you want to do here? There's 2 options, by the way. I remember helping somebody with this earlier today. What's one of the options? What do you want to try first? Now listen, the important thing that you can recognize that when you get a question like this, that you might not be sure exactly where to start. This becomes a really, really important skill to carry through Physics 30. Physics 20 to some degree, but especially through Physics 30. We don't know where to start. That's okay. That's going to happen. That happens to me from time to time, where I'm not sure where I'm going with a question. That's okay. Okay, it happens to the smartest people in the world. Try something, but not something random. There's no point in trying v equals d over t. You know it's not relevant. What have we done that seems relevant here? Well, when we talked about gravity, we've looked at 3 equations. There's the force of gravity. There's the gravitational field producer equation. There's the gravitational field experiencer equation. Now, is there a force of gravity between these 2 objects, the Earth and the astronaut? Yeah, this is valid. Does the Earth produce a certain gravitational field? Yes, the producer equation is valid. Does the astronaut experience it? Yes, the experiencer equation is valid. So what do we want to try? They're all valid. Try something. Worst case scenario is it's just not going to work and you're going to try something else. What do you want to try first? Javi, what do you want to try first? The middle one? Okay. Just so you know, guys, Javi picked the middle equation. There's no wrong answer to this, and there's no perfect answer to this, right? Okay, we could have picked any of the 3. Whatever one he said is the one that I was going to go with. Okay, I wasn't going to try to convince him of anything else. Okay, this is a valid equation. Whether it's going to work for us, we'll see. But it's a valid equation. It's not going to get us the wrong answer. Okay, let's figure out something from this then. G is 6.67 times 10 to the minus 11. What mass do we use there? The 5.97 or the 70? What's this mass? Go ahead. Sorry? Good. It's the mass of the producer, the mass of the Earth in this case. 5.97 times 10 to the 24. Divide that by r, which is going to be 6.6 times the radius of the Earth, which is 6.38 times 10 to the 6. Square that. Anybody have that value? Somebody must have calculated that already. 0.224. Thank you, Erica. Newtons per kilogram or meters per second squared. All right, it's not what we want. We want the force of gravity. We found the field strength caused by the Earth where the astronaut is. So did we just waste our time with what Javi suggested? No, Quinn, then what do we do? If we didn't waste our time, what do we do? The experiencer equation? Sure. It's a valid equation. If it doesn't work for us, fine. Try something else. Well, let's give it a try. We want to find the force. The mass, what mass do we use here? Mass of the Earth, the mass of the astronaut. 5.97 or 70? 70, the mass of the astronaut, the experiencer. And the gravitational field, or the acceleration due to gravity, what we're used to being 9.81, is this time 0.224. That should give us about 16 newtons. Good, done. So Javi's way worked. Even if he didn't know exactly where he was going, maybe he did. But even if he didn't know exactly where he was going with it, he tried a valid equation, and it ended up working for us. The other way that we could have done this is said simply, that first equation that I wrote down, we know what this is, we know what this is, we know what this is, and we know what this is. Guess what we would have gotten? What would we get? 16 newtons. Okay, this way it's quicker. It's a shorter method, but it's no more correct than Javi's method there. I don't care which way you do it. All right? That makes sense? All right, let's do just one more example with this topic, okay? So it says, what is the mass of a 60-kilogram student on Mars and the Earth? Sorry, we did this one. Any issues with the questions that we had on page 220 there? No, they're good? Yeah. Number one. Any others? Okay. Number one says, what would be the weight of a 22-kilogram dog at the equator on Saturn's surface? What's weight? Gravity, the force of gravity, right? Not the field strength, but the force of gravity. So what's the force of gravity at the equator acting on a 22-kilogram dog? There's a couple of options here, right? That last question that we did, we were trying to find, where is it here? Yeah, the last question that we did, we were trying to find the force of gravity acting on the object. We did that by using the producer equation and the experiencer equation, getting 16 newtons. We also did it by using the gravitational force equation. Pick one. Pick one here. How are we going to do that? Well, we can say F is equal to GM1M2 over R squared. 6.67 times 10 to the minus 11. And who was it? Javi, I think, in the last question suggested that I use the field equation first. Okay, that's fine. Try that again. Okay, I'm going the opposite way this time and trying the force equation first. Mass 1 would be the 22-kilogram dog. Mass 2 would be the mass of Saturn. What is the mass of Saturn? You guys had that from the table. 10 to the 26. Okay, so about 100 times the mass of the Earth. And what's the radius of Saturn? That's what we want, right? The radius of Saturn, the distance from the center to the surface where the dog is. 6.03 times 10 to the 7. And we got to square that. Okay, we do all the math there. It works out to be 230 newtons, which is only slightly bigger than it would be on the surface of the Earth. But wait, Saturn's heavier. Shouldn't it cause more gravity than the Earth? It does a little bit. but it's also bigger, which reduces it, right? So the two almost balance out. So gravity is almost the same. Good? Yeah. Uh, Say that again, Joe. From the surface of Saturn. No, this one's from the surface of Saturn to the center of Saturn. So we're talking about, look, you're on the surface of Saturn here, on the equator. Okay. The distance from the center of Saturn to you is that r that we use there, the radius of Saturn. That makes sense? We always want the distance from the center of the planet or the center of the producer to wherever the object is. So if the dog was way up here, I guess it doesn't look much like a dog, but if the dog was way up here, then we're going to want to use this distance right here. The distance from the surface to the center and the distance from the surface to the dog or the person or whatever right up there. Okay, always the distance from the center to wherever the object is. Is that good?